Hi, everyone. All right, so who was here last month? So a lot of you, cool. All right, so for those of you that were here last month, you were fortunate enough to have seen a talk by MC Quintessence on dark energy. And so at the end of her talk, she listed a ton of really ambitious big projects that are trying to probe the nature of dark energy. So today I'm going to talk to you about one of those big projects, HETDEX, which is the Hobby Eberly Telescope Dark Energy Experiment, and the heart of which lives right here in our astronomy department at UT Austin. Yay! So for those of you that weren't here last month or have forgotten, I'll briefly summarize what dark energy is. And so before the discovery of dark energy, we knew that our universe was expanding. So the Big Bang blew out a ton of matter and energy. But we also knew that, so the Big Bang blew out a ton of matter, and matter has mass, and things that have mass have gravity. And so we expected that the gravity between the matter would be slowing down the expansion of the universe. And so in 1998, two teams of astronomers went out to try to measure the rate of expansion of our universe. But what they found was that it wasn't slowing down. It was actually getting faster as the universe aged, which is weird. So basically there's some other big source of energy in our universe that we can't see. It doesn't emit radiation. We don't know what it is, so we gave it the term dark energy. So how do we study dark energy? It's dark, it doesn't emit radiation, so we can't observe it directly. But what we do know about it is that it's the cause of the accelerating expansion of our universe. So to start to probe the nature of dark energy, what we can do is try to measure the rate of the accelerated expansion of our universe. And so there's a few different observational methods for doing this. And one of them, so one probe we have to measuring dark energy observationally are called Baryonic acoustic oscillations. And so this is the method that HETDEX will be using to try to probe try to measure the accelerated expansion. And so basically, up until about 400,000 years after the Big Bang, our universe was pretty much just this big, hot, dense soup of particles. And disturbances in this soup of particles created something like sound waves or acoustic oscillations. And so eventually the universe continued to expand and cooled enough that these oscillations stopped and got frozen into what we call now the cosmic microwave background. And so this is a picture of our universe 400,000 years after the Big Bang, the cosmic microwave background. And so the colors in this image correspond to regions of higher and lower density. What you can't see with your eye is that the rings of these sound waves from our early universe are actually imprinted in this map. And so I drew a couple, there it is. So I drew a couple on here, very exaggerated ones, just to give you sort of the picture. But as our universe continued to evolve and expand, these rings that are imprinted on the cosmic microwave background expanded with it. And so a way that we can measure the accelerated expansion of our universe is by measuring how these rings grow, or how big these rings are at different points in time in our universe's history. And so if we can measure sort of the characteristic size of these rings at different slices in time, we can actually measure the accelerated rate of expansion of our universe. So what does this look like? So if we take a slice at a certain distance away from us, or that corresponds to a certain time in our universe's history, and we look at the distribution of all of the galaxies there, we can measure the average separation of a bunch of galaxies. And with statistics, we can measure sort of the characteristic separation of these galaxies, which corresponds to the size of these rings at that point in time. And so what we need to do is take these slices at different distances from us and measure the distribution of galaxies to try to measure the size of these rings. And if we can do this for a bunch of points in time, then we can map the accelerated rate of expansion of our universe. And so to do this really accurately, we need a huge survey of galaxies at a bunch of different distances away from us, so a bunch of different slices in our universe's history. And so HETDEX is going to attempt to do this. And so the HET in HETDEX stands for Hobby-Eberly Telescope. So the Hobby-Eberly Telescope is the 10-meter telescope at McDonald Observatory, and it's a telescope we'll be using to conduct this survey. And so the last part of this stands for Dark Energy Experiment. And so we're going to use the Hobby-Eberly Telescope to conduct a survey of over 1 million, or nearly 1 million galaxies in the next 5 years. And it's going to survey a sample of the sky right around the Big Dipper. And so basically, the Hobby-Eberly Telescope, so it's just a telescope, so it's a big light bucket essentially. But what we really need is an instrument, so something to collect the light from the telescope and give us data that we can use to map where all of these galaxies are, and a tool to measure the distance of these galaxies away from us. And so VIRUS is the instrument that's being built for the HETDEX survey. And so VIRUS stands for the Visible Integral Field Replicable Unit Spectrograph. So it's kind of a mouthful, but actually if we break this down, this acronym actually tells us a lot of information about how this instrument works. And so visible is just referring to the visible part of the electromagnetic spectrum. So basically, VIRUS or HETDEX is looking at the same wavelengths of light that our eyes can see. And so VIRUS, the instrument, is actually a spectrograph. So unlike an imager that's going to take an image of the field that the telescope is looking at, a spectrograph takes in the light from the field that the telescope is pointing at, it goes through a slit, and it gets diffracted off a grating, similar to how light goes through a prism and it gets separated into all its wavelength components, and then what you get, and then a detector takes an image of that spectrum. And so you get, for a classic slit spectrograph, you get a single spectrum for the entire field that the telescope was looking at. And so VIRUS is actually an integral field spectrograph. So it's a special type of spectrograph that takes the field that comes in, that the telescope is looking at, and it breaks it up into a bunch of spatial sections. And so VIRUS does this using fibers. And so basically, the light from the telescope, the field that it's looking at, gets separated into a bunch of fibers before it enters the spectrograph. And so basically, all these fibers are lined along a slit, just like it is up here in this traditional spectrograph, and the light gets diffracted through a grating the same way. But what you end up getting is, on your detector, instead of one spectrum, you get a spectrum for each spatial region. And so this is really important for HETDEX because we want to survey a ton of galaxies very efficiently. And so this means that when you look at a single field with HETDEX, there might be a ton of galaxies in there, and instead of getting just one spectrum for that whole field, you can actually get spectrum of a ton of galaxies with one pointing of the telescope. And so the last part of this stands for replicable unit spectrograph. And so this is actually where the real power of this instrument is. And so basically what we did is we built one fairly simple spectrograph, and then we replicated it 78 times. And so we basically made 78 copies of the exact same instrument. So basically this is a way of building a really massive instrument for a relatively cheaper cost. So each one of these 78 virus units or spectrographs is fed light through this fiber cable. And so this is the fiber cable, what the end of the fiber cable looks like. And so this is what the light from the telescope is fed into and goes into the spectrograph. So if we zoom in on this, we see, so this fiber bundle actually has 448 fibers. And so with 78 of these units, each being fed 448 fibers, that means that with one pointing of HETDEX, we're imaging almost 35,000 fibers at once. And so in a single field, you're not going to have a galaxy in every single one of those fibers, but you can imagine we can look at a lot of galaxies at once. And so how does this work? So what this looks like on the telescope. So here's our Hobby Arborly telescope again. If we take away the dome, so this is what the telescope looks like. So here's our 10-meter mirror. And on either side of the mirror, we have these big enclosures. And each one of these enclosures houses 39 spectrographs on both sides. And this green cable represents all of the fiber bundles that are feeding all of these spectrographs. And so you can imagine we have some galaxy or some field up in space that we're pointing the telescope at. So light is going to reflect off the primary mirror, and it's going to get, sorry, that's a really fast animation, but it gets reflected off the primary mirror, it goes up through a ton of optics, and at the focus of the telescope, that's where it meets the 35,000 fibers. And so the field gets broken up into all the fibers, and then all of those spectra are imaged in all of these spectrographs at once. So all of these units work simultaneously. And so here's just a zoom in. So each one of these little shelves in this enclosure house one of these spectrographs. And so the status of HETDEX right now, we have 16 units on the HET right now. And so we're in the process of commissioning these instruments. So basically what that means is we're taking some units out there, and we're trying to test them and test the telescope because a lot of upgrades needed to happen on the telescope to optimize it for this survey. So we're commissioning the telescope and this instrument at once and trying to figure out how running all of these units simultaneously works. So I have some kind of cool pictures I was lucky enough to go to one of the early commissioning runs. And so this is a single virus unit getting hoisted all the way up to this enclosure. This is a previous grad student watching one of the instruments he spent nearly 6 years building get hoisted 40 feet in the air. So it went well. There it is in its enclosure. So here's a bunch of virus units in one of the enclosures. And so this is the front side of the enclosure that faces away from the telescope. And on the back side, oh, I went backwards. So you can actually see these black cables are actually the fiber bundles being fed into the back side of each one of these spectrographs. And so all of these fiber bundles needed to be strung all the way up to the top or the prime focus of the telescope. So you can see this huge clump of fibers that are being strung up there. And so we have 16 units out there, and we're in the process of building, aligning, and characterizing the rest of them. So here's just a picture of one of our labs where we have a ton of these spectrographs sitting around. So HETDEX will use the virus instrument to survey nearly 1 million galaxies in 5 years, mapping the accelerated expansion of our universe when it was 1.5 to 2.3 billion years old. And this is going to help us probe the nature of dark energy. So thank you, guys.
All right, thank you, Feedback Fighter. All right, we'll take some questions. Right here. Two questions.
When the galaxies when the universe was 400,000 years old, it was shaped like an egg. Why is that?
You made a CMB like you started like an egg.
Oh, yeah. So it's actually a mapping of a sphere. So basically what we did is we measured the CMB by mapping all around us, I guess. So what that is it's actually a sphere mapped onto a 2D map. So it's the same reason why the map of the Earth is an oval, if that makes sense. Oh, yeah, sorry. He asked why. So I showed you the map of the cosmic microwave background, and it was an oval. It was like an egg-shaped. So he asked why it was egg-shaped. And it's because it's a 3D surface that's mapped.
All right, I'll allow the second question.
Yeah.
The question relates to the number of units you have. 78 as opposed to 80?
Yeah, so there actually are, so there's 78 virus units. And so there's actually 2 more units that are special. So they have slightly different gratings in them. And so those will be put on the same telescope. And those are sort of used for like following up galaxies. And so they're slightly different. They cover a slightly different wavelength range than the virus units, and they're higher resolution than the virus units. So they're not part of, so those 2 units aren't part of the HETDEX survey, but there'll be another instrument on the HET. And it'll be housed in the enclosure. So there's actually 80 slots in the enclosures. Yeah.
All right, ma'am, right there.
When will all of the 78 or 80 be installed so that the survey actually begins?
Yeah, so with big instrument projects, there's always delays, so it's hard to know for certain, but hopefully next fall.
Sir?
I guess more of a technical question as you're doing your survey. You find, I assume you already have the time slices like every 100 million years, every billion years, or you want to, you're doing slices times, like, are you doing 30 slices times, or 400, or what's the sample size?
Yeah, so you asked how many slices in time, I guess, we're looking at with HETDEX. So we're surveying a volume of area. So I showed you the 2D, like the field we're looking at. And so the volume that we're looking at is is from redshift 1.9 to 3.5. So it's when our universe was about 1.8 billion years old to like 2.3 billion years old. As far as how many slices we're going to make in between, I'm not actually sure. The details of how. Yeah. So yeah, I guess I'm not exactly sure on the details of how many like slices they make in between, how they're binning the distances. Yes.
Up front.
You might have covered this, but I forgot. Is there a reason why we picked that particular time frame?
Yeah, that's a good question. So yes, why we picked that particular time frame. So there's actually other surveys measuring baryonic acoustic oscillations, and a lot of them are looking, have made measurements very nearby. And so HETDEX is trying to push that further. So we've made measurements of baryonic acoustic oscillations in the nearby universe out to about maybe half the age of the universe. But HETDEX is trying to push deeper into our universe, and so it's trying to add a measurement, I guess, further back, if that makes sense.
As far as we can go, does that represent some kind of a limit, or?
Yeah, I guess it's the limit for the instrument that we're building, I guess, if that makes sense. So I'm sure there's a lot that went into deciding what type of instrument they would make and the specifications of that instrument, and I'm sure it was driven by how deep we wanted to go and could go, if that makes sense.
In the hat.
So when HETDEX is built and everything's running smoothly, we're getting our first set of data, what exactly about dark energy are we supposed to do? Are we going to figure out like maybe the units and the characteristics of dark energy, or are we going to find like a unit value of dark energy?
Yeah, so we're trying to measure the accelerated rate of expansion. So we're trying to measure the rate of expansion of our universe. So there's a bunch of different theories about what dark energy could be, and a lot of those theories, all the theories predict a different rate of expansion. And so I guess the simple answer is that by measuring precisely the rate of expansion of our universe, we can start to constrain theories.
Okay, one more.
What considerations went into choosing the part of the sky that you're focusing on?
Yeah, that's a really good question. Yeah, so what considerations went into choosing that particular part of the sky? Yeah, I guess Yeah, so, sorry, what?
It's always in the same, it's visible all year round.
It's a good point. Yeah. I guess I don't, yeah. Thanks. Yeah.
So was that supposed to, is it the same part of the sky that was chosen for the ultra deep field?
Is that the HST deep field? Do you know?
I don't know.
So the question was,
is
is that the same part of the sky that the HST deep field is centered on? Ava in the back, Dr.
Ava
Black
said no.
says
Yeah,
no,
I
it is
don't-
not.
Yeah, so there's, so if you can hear in the back, so there's a part of so it's a big field, but there's a part of that field that's called the Sheila survey, and so that overlaps with, like you're saying, 5 other surveys, and so the main science driver of HETDEX is dark energy, but there's a lot of galaxy science that can be done with the survey data as well, and so they'll use specifically that patch of the survey to learn more about galaxies.
All right. Let's thank Feedback Fighter one more time.